Welcome back. In this video we're going to talk about the general parametric equation for an ellipse in R2. Recall that in a previous video we talked about the scalar equation for a circle which had center h, k and radius r as given by x minus h squared divided by r squared plus y minus k squared divided by r squared equal to 1. And then we used the Pythagorean theorem and the definition of cosines and sines to translate this scalar equation into a vector valued function, which we called r of t. This vector valued function had x coordinate x of t and y coordinate y of t, and each of these functions were given as such. We actually derived that. This t was called a parameter, and these were known as the parametric equations, there are two of them, for a circle in R2. We then went on in our previous video to talk about an ellipse, which is an oblong circle, a circle with two foci, rather than just one center, which we haven't really talked about. But we saw that the scalar equation for an ellipse centered at h, k, with x semi-axis length x is equal to a and y semi-axis length equal to b was given as such, which is almost identical to the circle, except instead of r squared in each denominator, the denominator on x is a squared and the denominator on y is b squared. Let's convert this into a vector equation for an ellipse in R2. And instead of deriving this, I might just let it drop from the sky. It's one of my least favorite things to do, but this is for exposure. So we write r of t. R of t will have two equations, one for the x coordinate and one for the y coordinate, each in terms of t. And we will say that this is going to be h plus a cosine of t, where the y value would be k plus b cosine of t. This is what we would call the x of t value. And this is what we would call the y of t value. If we want a full rotation, if we want an entire revolution to go the entire ellipse, we would set t to be between 0 and 2 pi, since we're thinking about t as the angle of incidence for the vector drawing the external boundary of the ellipse. Perhaps we should take a look at an example in Mathematica to get our head around how this works. Let's switch over. Here we are in our lesson 5 examples. In this case, we're going to need a center for our ellipse. Let's go ahead and define the center to be 0, 0 to begin with. So here is 0, 0, h, k. We're also going to need a x semi-axis and a y semi-axis. Maybe we say it's going to be 5 in x, and we'll say it's going to be 1 in y. In this case, we're going to do a vector equation for the line, so we'll use parametric plot. And then we'll go ahead and end the parametric plot command. Okay, just good commenting. Remember we said that the parametric equation would be h plus a cosine of t, and that's going to be a multiplication. And then we would, the second y coordinate was k plus b times sine of t, and we claimed that we wanted t to run from 0. Oh, I broke my own cardinal rule. The moment I do an open bracket, also do a closed bracket. T runs from 0 to 2 pi. Let's go ahead and graph. There we go. We can also set the plot range just to make this super clear, and perhaps we would go from -6 to 6 in the x direction, which means I want to determine x first, comma, let's now do the y direction. Let's do the same size in the y direction. All right. Mathematica is automatically controlling the tick marks for me. Maybe I want to specifically tell Mathematica the exact ticks that I want. To do so, we've talked about using table. Here we'll use table, and we'll say, please produce for me all i's, where I runs from -6 to 6, so that I get the entire tick marks. And we will do 2 copies of that. We'll do the x copy and the y copy. If I change my y, notice that I would get less ticks. So here this table runs from -6 to 6, and you see that that's the x. The second table here runs from -3 to 3, and that's the y. If I want the graph to be labeled the same in the x and y, I can just use the same table over again. Here's the ellipse that we said. We see that the y semi-axis is of length 1, the x semi-axis is length 5. We can go ahead and change this now. Let's change this to 2, and we'll shift down 1, and we'll say that the x semi-axis is 2 and the y semi-axis is 4, so it should be longer. Right. And maybe we would want to graph the center point just to make it super clear where that center point lies. So we'll use the show command to combine. We'll use the graphics command, which allows us to graph primitives like a point. So here's graphics. We're going to go ahead and open and close brackets. We'll say our point size, we're old pros at this now, right? 0.02. And the point that we're going to graph is going to be called C. And we actually need to define what C is. C is equal to the point h comma k. And let's suppress that output. So now we go ahead and graph. Oh, there's the graph of C. And I can change this around, right? I can say, oh, let's go to the negative in x. And it gives you a sense of how these parametric equations or vector valued function description of an ellipse works. In the next video, we're going to talk about vector valued equations that output into R3. See you there.